So, we have discussed ferromagnetism. Now, we shall discuss antiferromagnetism. So, what we mean by antiferromagnetism is that there is a two sublattice in a given crystal lattice system, in which one sublattice, call it as A sublattice, we will make these discussions more clear. A sublattice contains primarily upspin density or predominantly upspin density, and the other sublattice, call it a B sublattice, contains predominantly downspin density, which means downspins. So, you have ordering. So, this ordering is up down as you go from one lattice site to another, and this is called as the antiferromagnetism. So, we will discuss antiferromagnetism. And again we shall talk about a Hubbard model, which is what we have done earlier, and the Hubbard model is once again, for convenience, I am writing it as the kinetic energy term, which is the first term, this term, which is neighboring sites, hopping between neighboring sites I and j, and sigma is the spin. So, this angular bracket over I j that you are seeing here denotes that they are neighboring sites. So, hopping is over the neighboring sites, and then we have an interaction which goes as n I up and n I down and runs over all sites I. So, this is the interaction between the densities at a given site. So, this is an on-site interaction between taking place between upspin density and downspin density. We cannot have upspin at a given site, which is excluded by the Pauli's exclusion principle. And so, similarly, now the problem with solving this model is that you have this term as a two particle term, which we know that kinetic energy operators is actually a two body operator, or rather a one particle operator in that sense. So, it causes hopping from one site to another, whereas if you open this term, it will be a four body operator, and written together you can't find a suitable basis so as to solve them exactly. So, we will not talk about exact solution, but rather what we should talk about is mean field or an approximate solution, and this mean field solution that we are going to talk about now is called as a Hartree-Fock approximation. So, let us see what Hartree-Fock approximation means. Now, this will be again discussed at length when we do the Green's function problem. So, Hartree-Fock approximation. So, by this what we mean is we will write down the interaction term, call it H int, and so this is as it is written above, it is n I up and n I down. And we have discussed this several times that the electron density operators can be written in terms of the single particle electron operators as C I up dagger C I up and a C I down dagger C I down. So, by this approximation what we are going to do is that we are going to split this 4 operator term into 2 operator terms and take all possible combinations that come our way. And so, this H int Hartree-Fock is equal to u, there is a sum over I, there is a sum over I, and I will take this A I up dagger A I up and plus. So, the combinations are taken with these two, and then the combinations will be taken between the first and the third. So, I will have a term such as Ci up dagger Ci down, and then there will be a combination taken between. So, this will be this should come in with a negative sign because you have changed one electron operator, you have swapped the Ci down with the Ci up. So, this should come with a negative sign, and so this is a negative, and then there will be a term which is between the first and the fourth, which is again sorry, this is dagger, and then there will be one between the first and the fourth. So, that causes two swaps which would eventually get me a positive sign. So, that is a Ci. So, I'll write it once again. I need bigger space. So, we'll just let me erase this, and so that we can write it slightly elaborately in the next page, because I would need a larger space here. So, I am cutting it out, and let us just go to the next page and write down this. So, H int H f would be u and Ci up and a Ci down dagger Ci down plus a Ci down dagger Ci down and a Ci up dagger Ci up. Now, there will be a minus sign, because so there is a Ci up dagger Ci down, and this comes with a Ci down dagger Ci up, and so this and another term which is minus Ci down dagger Ci up dagger Ci down. Now, you see, by doing this we have converted. So, what we have done is that we have taken expectation values of two of the operators at a time, so that the Hartree-Fock Hamiltonian can be reduced to a uniformly two body term, or just like the kinetic energy, so that we can find out a basis and can diagonalize them. So, the 4 operator term has been decoupled into sort of taking an expectation value of two of the operators at a time, and we have taken all possible combinations in doing so. Now, it so happens that the terms which are the first two terms, that is this terms, are important for considering antiferromagnetism, whereas these other terms are not important for antiferromagnetism, but they are important for something else, which we will see later. If we drop these two terms, and of course, there is another term that we are dropping, is that when we have the expectation of all the 4, that is 2 at a time. So, there will be a term which is so neglected term is which is like terms such as this. So, Ci sigma dagger Ci sigma or sigma prime, and there is a Ci sigma prime dagger Ci sigma. So, the expectation of, so these are constant terms, because we are taking the average values of each of these two, and it just turns out to be a constant, and which is dropped from the problem. But however, so this total or rather this Hartree-Fock the interaction term is written as u into Ni up Ni down and plus Ni down Ni up. and this is our Hamiltonian that we are going to look at along with the kinetic energy term. So, now consider a specific case as an antiferromagnet. So, consider an antiferromagnet, and what we mean by antiferromagnet is that as I said earlier, that there are two sublattices A and B, and so when a site is that of a sublattice, then it contains predominantly upspin, and a site B, it contains predominantly downspin. So, if that is the case, then we have so an upspin Hamiltonian feels a potential U into downspin, average downspin densities, and similarly a downspin Hamiltonian feels a potential U into upspin densities. So, if we introduce notations such as the total density being, so n up and its I belonging to either A or B plus n down for I belonging to either A or B should be equal to 1. So, the total density of upspin and downspin should be equal to 1. As we said that A contains predominantly upspin density. So, if the site is I site belongs to that of A, n up would be much larger than n down, and vice versa, if I belongs to a site in B, then n down will be much bigger than n up, but however, both of them put together should give me 1. And we can also introduce magnetization, which is given as the difference in these two densities. So, A B minus n down I A B is equal to m. Now, this could be the way it is written, it could be plus m or minus m depending on whether we are on the A sublattice or B sublattice. If we are on the A sublattice, then the upspin density will be bigger than the downspin density, and in which case m will be positive, and otherwise we will have a negative sign here. So, you can see that this whole scenario can be slightly simplified if we write the m as minus 1 whole to the power I into m. That means that if we start scanning the lattice site as 1, 2, 3, 4 etcetera, we will alternately get A, B, A, B, A, B and so on. So, depending on whether we have m I equal to even, then we will have m equal to positive, and if we have I equal to odd, then we will have m equal to negative. So, this is the situation. So, let me go back once again and just let you know that what is my system. So, we are planning to study antiferromagnetism, and we have written down Hubbard model, and we want to understand antiferromagnetism from the Hubbard model, just like we have understood ferromagnetism from the Hubbard model. Now, as I said that this Hamiltonian cannot be solved exactly, because one contains 2 electron operators, the other contains, the second term contains 4 electron operators. So, there is no suitable basis where you can solve it. One can of course do an exact diagonalization of the problem, which is often done, but it is usually for a smaller number of sites. And we want to do it analytically here. So, we employ a Hartree-Fock approximation, which is equivalent to splitting this 4 operator term into 2 operator terms, and if we take unrestricted combinations, we get 4 terms as it is shown here. Let us call this as equation 1, or maybe we can call this one as equation 1 and this one as equation 2. So, in equation 2 we have taken all possible combinations, and we have said that only the first 2 combinations are relevant for studying antiferromagnetism, and the other 2 combinations are not relevant immediately, because they correspond to how an upspin is correlated with an upspin creation operator is created with a downspin annihilation operator and vice versa, and these are not relevant for studying antiferromagnetism, because here we are interested in to see that how a downspin, what a downspin potential is and what an upspin potential is, so that we can write down a Hamiltonian separately for an upspin or a downspin. So, this is the form of the Hartree-Fock Hamiltonian, and let us make an assumption to begin with that there are 2 lattice sites A and B, and the whole system is formed of interlacing these 2 sublattices, A and B sublattices. A contains predominantly upspin, there could be a small downspin density, but very small, and B contains predominantly downspin density, and it could also have a small upspin density. So, now to make notations clear, we have written down the total density for I to be either in A or B sublattice equal to 1, and the magnetization is defined as this. Now, we have to solve this Hamiltonian, because now we have been able to write it in terms of 2 operators, 2 fermion operators for each one of the terms that appear there. So, for upspin, V up I equal to u into downspin density, as we have written, which is equal to, now from this I solve for each one of the densities. So, these are really the average values that appear there. So, these are averages. Okay. And this is equal to u by 2 minus u m by 2 into minus 1 whole to the power I, by solving these 2 for each one of the n up and the n down. And for downspin, my potential for a given site is u into the upspin density, which is equal to u by 2 plus u m by 2 into minus 1 to the power I. So, these are the potentials for the upspin and the downspin, and we have also written it down in terms of m, etc. Now, we can also define a quantity called as delta. So, define delta, which will say eventually that it is the magnitude of the gap for an antiferromagnetic insulator. It is u m by 2 into minus 1 whole to the power I, that is the second term that appears above, and let us keep numbering them. So, let us call this as number 3 and number 4. So, in equation 4 the second term would be replaced by delta. So, that again a V up for I belonging to A sublattice is equal to u by 2 minus delta, and this is same as V down for I belonging to B sublattice. Okay. So, there is a sublattice symmetry which you can see it from here. So, the upspin potential for I to be a part of or I to be in the A sublattice is u by 2 minus delta, which is same as the downspin potential for I to be in the B sublattice. And similarly, V up for I to be in B sublattice is equal to u by 2 plus delta, which is same as V down for I to be in the A sublattice. And suppose we write this, now we can write down the Hamiltonian for each species of spin, that is say for upspin. So, let us write down a upspin Hamiltonian to be simply H up I, which is equal to a minus T I j. Now, since we are writing it only for upspin, we should not write sum over sigma, but it is C I up dagger C j up plus V up and I, and it is a N I up, and this is nothing but C I up dagger C I up. So, this is the Hamiltonian for the upspin for I to be any lattice site. I can belong to either A or B, and if I belongs to A, then surely J will belong to B, and the vice versa is true. That is, if I belongs to B, then J will belong to A. Now, this way we can also write down the Hamiltonian for the downspin exactly in the similar manner, when we will have simply all these ups will be replaced by downs, and we now know what V up and V down are from the definition that we have given in equation 5. Let us call this is equation 6. Now, in order to solve it, because we have two sublattices, we can write as this Hamiltonian as a 2 by 2 Hamiltonian in the sublattice basis, and for that we will have to transform into the momentum space, and the momentum space Hamiltonian H up of k is written as k epsilon k C k up belonging to A, C k up dagger and C k up in belonging to B, and we will have a plus and minus delta term. This is for C k up belonging to A, C k minus q up belonging to A, and we will also have a term which is delta and a C k up belonging to B dagger and C k minus q up belonging to B. So, this is the upspin Hamiltonian. Now, the sublattice indices are made explicit in the superscript, and there is of course also a constant term which you will be able to find, and we will write it, but the constant term, as we said, is dropped and it is not considered in our problem, because that will just shift the energy up by a constant amount or down by a constant amount, it will simply shift. So, it is not important. So, what is important is that we should now be able to write down a 2 by 2 Hamiltonian from the Hamiltonian that appears in 7, and so write it, the task is that write H up k in sublattice basis. And so, this H up k is nothing but minus delta epsilon k. Let me take out a bit more space here and so that I can write down the basis also, which will help you. So, this is minus delta epsilon k and delta, and now you will have a C k, it is written in C k up dagger A and C k plus q up dagger B. So, it is in that. So, it is C k up A and C k plus q up B, and sorry, this is not plus, this is minus, we have written that as minus. So, this is minus and minus here will. So, there is a minus sign here and there is a minus sign here, and of course, there is a term which we have neglected, and we have said that we are neglecting it, is a term which is like this, and this is say equation 8. Equation 8. So, now we can, so it is 2 by 2 Hamiltonian, and it can easily be solved. Let me write down the Hamiltonian here. This can be solved with the energy eigenvalue. So, I am neglecting this part because it is a constant, and so E k, if you solve this with this, you know how to solve the 2 by 2 matrices and find the eigenvalues. So, E k up becomes equal to plus minus root over delta square plus epsilon k square. And similarly, your H down, so this is my equation number 9. So, H down k without the constant term can be written as delta epsilon k and minus delta, and we will again have the eigenvalues as E k down, which is same as E k up, and this is equal to plus minus root over delta square plus epsilon k square. So, this is your solution of the problem, so to say. So, we have been able to do a Hartree-Fock decomposition of the Hubbard Hamiltonian and have been able to write it as a 2 by 2 in the sublattice basis, a 2 by 2 matrix in the sublattice basis, and then diagonalize it to find that there is a symmetry of the up and down spins. Both give me eigenvalues which are same as plus minus delta square plus epsilon k square. Now, this tells me that this gives rise to density of states. How do we calculate density of states? The density of states is calculated as n of epsilon, which is equal to delta of epsilon minus say E k, and this is, if you like, that this is can be written as there is a sum over k, and it has to be divided by the, for the normalization, the number of k points, and so this is like a sum over k and limit eta going to 0 and something like eta divided by epsilon minus E k whole square plus eta square. This is usually done when you have to calculate the density of states, which is a delta function, and the delta function will give me a peak as soon as the energy will hit a particular value of E k, and E k will have a range of spectrum of values over the full Brillouin zone, and if you are, we are talking about a square lattice, we have a Brillouin zone from minus pi over a to plus pi over a, where a is the lattice constant. And in order, now this, in order to calculate it computationally, a delta function can be, delta function is ideally just a straight line having a peak, an infinite peak at particular value of this x axis here, whenever omega will hit a k, I will get a peak, an infinite peak, so to say, and I will have to sum over all these k's in order to calculate the total density of states. So, it can be computationally calculated if I give it a small width to this by expressing it as a Lorentzian. So, this is a Lorentzian, and this will help us to calculate the density of states. And this density of states come out as, so this is, it will look like this, and so this is the occupied band which is below the Fermi energy. So, this is the Fermi energy, and this is the, basically we are plotting the density of states versus energy, energy E, and this is plus delta and this is minus delta, and we have empty hole band which is here. So, this is empty and this is filled. So, this is the it is called as a particle band. So, it is filled, and this is called as the hole band, and that is empty. Okay. So, this is the density of states, and this is where the Fermi energy lies. So, I will write it here, the Fermi energy instead of there. That is the density of states versus energy plot, and sometimes you will find that this is the axis is turned, that is in the x axis you will have energy and the y axis you will have density of states, but it means the same thing. Now, you see that remember that we have a 2 delta equal to u into m minus 1 to the power I. So, if u goes to 0, that is if you switch off the interaction term in the Hubbard model, then you will have only kinetic energy. So, which means that this gap will go to 0, the gap that appears here. So, this is the gap. So, this gap will go to 0 and will have a system which looks like this, which is a metal. Okay. And so, this is my EF, and this is for u equal to 0. So, these are all occupied, and it corresponds to a metallic regime, because you have only so the whole states are empty, but they are infinitesimally close to the particle states. So, there are transitions possible between the particle states and the whole states. The interesting thing is that as soon as an infinitesimal u is switched on, so I will write this because this is important, as soon as an infinitesimal u is switched on, a gap opens up. And we have an insulator. But remember, we have started with an antiferromagnetic system. So, that antiferromagnetism has to show up. Now, going back to this formula, we can now drop the minus 1 whole to the power I and only consider the magnitude, because we know that it will vary from one side to another. It will alternately become up and down spins depending upon whether you are on an A sublattice or a B sublattice. Now, in this problem, you have been able to diagonalize it and found out the eigenvalues, but what about the eigenvectors and what do they give us? So, let us try to find the eigenvectors. So, let us calculate the eigenvectors and do a little bit of algebra to find out the eigenvector. Let us call them as alpha k and beta k for the upspin. Similarly, they will be there for the downspin as well. So, this we only can calculate one of them, because the other one will obey the orthonormality condition, which says that alpha k up square plus beta k up square equal to 1. So, suppose we calculate only beta k and say that alpha k is simply equal to this, and beta k comes out to be this. You have to do it. You have to put one of the eigenvalues, say plus eigenvalue, and then do it, and then also do it for the minus eigenvalue. So, we are showing it for the negative eigenvalue, which is equal to epsilon k square plus delta square. You can also do it for the positive eigenvalue. Things will not be anything different. So, I have a epsilon k up minus a delta whole square plus a epsilon k square. So, this is my amplitude, and of course, the state will be some amplitude into some space part, and so that could be a function of r in some trivial or some non-trivial manner. So, this is your and then you can calculate the magnetization. So, magnetization is m, which is equal to n up minus n down. You know that we are talking about a particular site. Now, here we are talking about a upspin or a sublattice site, and this will be nothing but equal to 2 over n. I will tell you why it is 2 over n, and k. Now, I will have to sum over all k, but which k's? The k's that belong to the filled band, that is a lower, let us call it lower Hubbard band, or lower band would be fine, and this is equal to alpha k up square minus alpha k down square. Why it is 2 over n, which means it is 1 by n by 2. The reason is that n is the number of sites, and n by 2 is the number of unit cells. And so, we are actually summing over the unit cells. Is that clear so far? So, we are talking about the magnetization, which is the upspin density minus a downspin density, and how do we find those densities? We will have to sum over all occupied levels, and we are summing over only the levels which are occupied, that is the whole levels are empty, and we have n sites of course in the lattice, but there are n by 2 unit cells, because each unit cell contains 2 sites, each one of A and B. So, a unit cell contains a sublattice and a B sublattice. So, this is a and this is a B sublattice. So, this is the unit cell for the problem, and that is why we are summing over the unit cells, and that is why there is a 1 divided by n by 2. So, this 2 by n came from 1 divided by n by 2. So, this factor has gone in here. So, then we can solve for this, and what we can get, or what we shall get, is the following. So, we will get m as 2 over n, and you should work it out to get this as delta over E k. So, we are taking a difference between the upspin densities alpha k up square minus alpha k down square at a given site, which is predominantly containing an upspin. Okay. So, alpha k down square is in principle very small, and alpha k up square is large. So, that I should get a magnetization which is close to 1, and let us see that what happens when we have. So, this is nothing but equal to 1 by n and sum over k and m u over E k, because my m u equal to 2 delta. This we have defined it earlier, and since m is not equal to 0, I can cancel m from both sides and I will get 1 equal to 1 by n u over E k, or this is recasted in the form that 1 over E k is 1 over n k. Now, k belonging to the lower Hubbard band, I will write it here, LHB means a lower Hubbard band which is occupied. So, this is equal to 1 over E k. So, just like the Stoner criterion, we got a self consistent criterion for antiferromagnetism, which is similar to the Stoner criterion that we have obtained in the last discussion. So, that is my self consistent equation, and I should this is the condition for antiferromagnetism to occur. Now, let us see a specific case which is of importance. Let us call C the strong coupling limit. And by strong coupling limit, what I mean is that u is much greater than t, and in principle one can just simply say that u tends to infinity. So, the fermions or the electrons are extremely correlated at a given site. So, it becomes energetically impossible for if there is an upspin at a given site, a downspin to come and sit at the same site is nearly impossible. So, this means that implies that it is energetically unfavorable for electrons of opposite spins to occupy the same site. So, if this is the case, this is called as a strong coupling limit and or rather strong correlation limit, in which case what we have is the following, that we have delta which is equal to m u over 2 is very large, because u is large. And in which case, let us look at the beta k that appears there. So, we have equation 9 there, and let us call this as equation 10. So, the equation, so beta in equation 10, let us call this as equation 11. So, beta in equation 10 or beta up or beta k up in equation 10 takes the form. So, beta k up is equal to epsilon k divided by root over of E k minus delta whole square plus epsilon k square. Now, for E k to be which one to consider. So, if we take E k to be minus delta. So, you see here is E k equal to minus delta. So, we take the top of the filled band. So, top of the filled band, then I have, if I put it here, then I get a minus delta whole square, which gives me 2 delta whole square, which is 4 delta square, and that can certainly be much greater than epsilon k square. So, epsilon k square can be neglected in the denominator. So, I will get a beta k up to be equal to epsilon k divided by 2 delta. And this is, since delta is large, beta k up is very small, and this is what we expect, that a sublattice being a sublattice which contains predominantly upspin, the beta k up will be very small, and and then what we have is that alpha k up in that case will almost be equal to 1, because alpha k is since alpha k up is root over of 1 minus beta k up square, and this is nearly equal to 0. So, alpha k up becomes equal to 1, and if that is the case, then my m becomes equal to 2 over n and sum over k. Now, you see that it had this had mu over E k. So, I can write that as simply as E k to be. So, this can be written as this sum and 1. So, this is equal to 2 by n into n by 2, because sum over k, k over all unit cells, and you are summing over 1, which means you are summing over the number of unit cells, which should give me 1. So, this is my magnetization. So, magnetization is equal to 1, which means that n up minus n down equal to 1, which means n down equal to 0 and n up equal to 1, and the self consistency condition becomes equal to 1 by u equal to 1 by n sum over k and 1 over 2 delta. Now, you see that E k becomes, E k is same as E k minus delta, and that is equal to, so square root and so on. So, this is equal to 2 delta. So, this is the self consistency equation, and this is nothing but equal to 1 over 2 delta, because of, since you have sum over k summed over 1 gives me equal to n, and this is the self consistency condition is that the 2 delta becomes equal to u, and that immediately says that m equal to 1. So, in the strong coupling limit, the magnetization is is 1. This is a magnetization per site, the way it is defined as its Ni up minus Ni down. But however, Hartree-Fock picture is somewhat away, or somewhat sort of the realistic picture would be there will be some quantum fluctuations associated with it, because it is a mean field picture or an average field picture, and this because of the quantum fluctuations, this value of the magnetization goes down, and these quantum fluctuations we are not including it, but we will learn later how to include quantum fluctuations. So, quantum fluctuations reduce this value to 0.6 in 2 dimensions. So, in 2 dimensions the fluctuations are large. So, these quantum fluctuations actually reduce the value by 40%, and the magnetization will be in the strong coupling limit, the magnetization will be 0.6, that is a sublattice magnetization. So, this gives rise to an antiferromagnetic insulator. As soon as you switch on a U, it will be an insulator, and each site will order the A sublattice will have upspin density, B will have downspin, A will have upspin again, and B will have downspin. And this corresponds to ordering wave vector, which is given by, so ordering wave vector for the spin orientation is q equal to pi. Let us just try to see it in one dimension how it looks like. So, in one dimension we will have sort of so this enables us to write S q equal to some S and 0 and exponential I q dot r. So, this is how the profile will go and so in one dimension if I take a exponential I pi x as the modulation. So, this I pi will give me a negative sign. So, as I go from one side to another, I mean I will have to write this as a delta. So, this will be a delta. So, how the, if I have an upspin at a given site I plus delta, I have a downspin, right. So, the ordering becomes, so as I go from up I to I plus delta, I should get from the ordering of the spin, the spin vector will change its orientation from up to down, and that is why this pi, that kind of a ordering will come. And this can be actually probed in the neutron scattering experiment. So, the neutron scattering experiment will detect these eigenvector and see that there is a ordering of this kind in the two dimensional plane. It is so, in order to do neutron scattering for a two dimensional thing, one has to actually take a small angle neutron scattering, so that you can see the surface well. So, the spin orientation in the surface.